when you have just a random set of ordered pairs and they do not orientate themselves into a right triangle. Okay, so these 3 points that we saw on the last 2 pages do not create a right triangle. Okay, even if they did, this process would still provide the circumcenter, but hopefully you realize that there's an easier way. Does that make sense? Okay, this process that I set up here on these 2 pages will always work 100% of the time, regardless of the 3 points that you're given. However, there is a special case where maybe it takes, it proves to be useful to decide whether it's a right triangle or not. Okay, because if it is a right triangle, that work is so much less involved than what we're about to do. We're going to be doing this quite a few times in the next couple days. So if you struggled on this, my hopes are is that you take some pretty good notes here so that you can then kind of reference those in tonight's homework and maybe tomorrow's homework and maybe the next day's homework. Okay? So first thing I want to do, you can do all this stuff without any graph. Okay? I just think that my graph does a couple things for me. One, it organizes my information in regards to what I need to find and what I have already found. It also provides a little bit of confirmation in regards to whether I'm doing things correctly or not. Okay, so I'm always going to try to plot these things. Now, some of you said you've used GeoGebra, which is 100% fine, but hopefully we're using GeoGebra in the event of checking everything we've done by hand, because GeoGebra will disappear on tests and quizzes. It disappears on the end-of-course exam, and you have to show things by hand. You have to show work on the end-of-course exam to get credit. Okay, so we need to be able to do this by hand. So I'm going to just graph these points real quick. So we get 4, 2 as point A, 6, negative 4, point B, and then negative 2 is point C. Okay. Construct that triangle then. And the more time and effort you put into creating this to where it's, using straight edges and stuff like that, obviously some people maybe use a line like that, and it's a little bit off, right? So everything else will be a little bit off. Shouldn't be terrible, but try to be kind of clean with your graph over here. So we're going to walk through these 3 steps. So hopefully you recognize that these 3 steps, or I guess 4 steps here, are the same as the 4 steps here, which are the same as the 4 steps here, right? So if you can do this once, if you can find the perpendicular bisector 1 time, there's absolutely no reason why you shouldn't be able to find it 2 times, 3 times, 4 times, 5 times, because it's the exact same process. Okay. First thing says we're going to find a perpendicular bisector of AB. Okay. So we got A located at 4, 2, B located at 6, negative 4, and I want to find slope. Remember, slope, formula-wise, is that, right? And I know some of you want to count, but remember, there will be times where you can't count. All right, it doesn't make sense to count. Maybe if there's fractions here, or maybe one of these points is like pi, and you can't really count that. Okay, so you need to know the formula. So subtract your y's. So I'm gonna go 2 minus negative 4, and then 4 minus 6. So what's that give me on top? 6, and what's it give me on the bottom? Negative 2, and that then simplifies to negative 3, right? Okay. So the slope of A to B is negative 3. Now, here's why I have the picture. If I go from A to B, am I going left to right? Am I going down, or am I going up? A to B. You're going down, right? And shouldn't that be mimicked with my slope of being negative? Left to right, when your graph goes down, your slope should be negative. So we know that maybe that's confirmation that we've done something probably right. If I want to find the slope of any line that is perpendicular to AB, we now know slope of AB is negative 3, so what is the slope of anything perpendicular to it? Opposite sine reciprocal, right? So that would be 1/3. Okay. The next thing we're going to do is find the midpoint of AB. Well, the midpoint of AB, okay, it's an ordered pair, x comma y, such that you take your endpoints, add them together, divide by 2 for both coordinates. Okay, so what do we get here? Add these together, divide by 2, you get 5. Add these together, divide by 2, you get -1, right? All right, so once I collect that information is going to be what is going to help us develop the equation for the perpendicular bisector. I'm just going to go to my picture real quick and use this information real quick. I'm going to plot 5, -1. And 5, -1 is right there. Does that look like a midpoint of AB?
Yeah.
So probably visual confirmation that I've done that right, correct? If I would have found like 5, 1, go over to 5 and up 1. Oh, not up 1. Does that point look like the midpoint of AB? Not even on AB, right? So that would have been visual confirmation telling me you've done something incorrect, okay? I look at the slope of 1/3, and that's the slope of a line that's going to be perpendicular to AB, right? Well, I know this point here of 5, -1 needs to be on this perpendicular bisector. If I go up 1 and over 3, put that point, and then go down 1, left 3, put that point, and then connect these things with a line. I'll just use we'll color it here in a moment. If I use that line right there, does that line look like it's probably a perpendicular bisector of AB?
Yes.
Yeah, it looks perpendicular. It looks like there's going to be a right angle there, and it is definitely going through that midpoint. So that red line is going to have the components of a slope of 1/3, and it's going to incorporate the point 5, -1. And that's why I put the graph there. That's why I organized my work that way. So that before I even do anything, I know that what I'm about to do at least uses the right things. Okay? We're going to use that formula to create the equation for this line. And just kind of going back, understand that this is one problem, right? But inside this one problem, there's probably, I don't know, 10, 15 other individual small component problems, right? Okay? If you, finding slope in Algebra 1 was one problem that you did a lot of, okay? Then finding midpoints in Chapter 1 of this class is one problem we did a lot. Now we're combining all those things and doing them together to solve a bigger problem. In all those other smaller problems, you had abilities to check your work, okay? I would be very upset with myself if I would go through all this work and I made an error on that -3 when I found the slope, and I made it +3. So I make that slope +3 on part A of number 1. The first thing I did, I go through all this work that might take us 10, 15, 20 minutes to do. Everything is wrong because of that +3. Does that make sense? So when you complete one task inside a large problem, and you have the ability to check that task, check it, okay? Periodically going through and make sure you're doing everything right so that, if I make sure every component is correct, the whole problem should be right, okay? If you guys go to, like Ford or GM or something like that, and you can see their assembly lines, do they just put all this junk together, all these parts put a car together, and then just go out in the lot, and hopefully when they turn the key, it turns on? Or does at every stage do they start checking things? Okay. Every time they insert maybe an electrical component, they check to make sure it works. They put in another electrical component, they check it to make sure it works. Okay. They put in their brake system, they check it to make sure it works. And if they've checked, along that line, everything that they've put together, then they know automatically that when they go out the lot and they turn the key, it's going to start. Okay. So that's kind of the idea that I want you guys to kind of think about as you're doing these long problems. Now plugging in the components here, y minus y1 equals m times x minus x1. Obviously this then is the x1 and y1, and this is the m that we need to use here. So we go y minus -1, slope of 1/3, and then x minus x1, which is 5. Okay. Minus the negative becomes plus, right? I'm going to distribute my 1/3 through. So I get that. 1/3 times 5, those are fractions, right? 1 times 5 gives me 5. 3 times 1 gives me 3. Now I need to move the 1 to the other side. So I'm going to use subtraction, so I'll subtract 1 from the left, that goes away. And then you'll subtract 1 from over here, right? Okay. Well, would you guys agree that these two things are like terms? Okay, they're both constants, right? And I need to combine those. And how do you add or subtract two fractions? You need a what? Common denominator. What's the common denominator going to be between those two numbers? It's going to be 3, right? Can I rewrite 1 as 3 over 3? Still 1, right? Okay. Now that I have a common denominator of 3, I can actually do the algebra with the numerators. So I get y equals 1/3 x minus -5 minus 3 is -8, and then over 3. And that is the equation that you want. Okay? Leave it as fractions. Okay? Because if I look at those two numbers, 1/3 and -8/3, they are rational numbers, but they're a unique type of rational number in regards to that they don't terminate, right? They repeat forever. 0.3333333 minus 2.66666666666 forever, right? Okay. Now let me show you something kind of geometrically in regards to what that means if I were to do some maybe haphazard algebra here. We have y equals 1/3 x minus 8/3, right? That's the line we want. Okay, now if I would actually have typed in y equals 0.33x minus 2.67, okay? Now you're seeing that, GeoGebra took what I typed in initially and wrote it as decimals. It approximates it, doesn't leave it as the 1/3 or 8/3. But the graph is using the 1/3 and the 8/3. And if I look at these two lines, zoom in far enough, you see that they are different lines. Does that make sense? Okay. So when you round something, when you round a fraction as a slope, or you round a fraction that is your y-intercept, okay, you are creating a completely new line. Now, zooming back out, those two lines are pretty close to one another, right? Okay, it looks like they're one when you're zoomed out into, a view like that, okay? But zooming in, they are different lines. They're pretty good approximations of one another. However, if I do that, and then maybe I round another equation, and then I go through the work to find the place where these two equations or these two lines intersect, I will not have the intersection of, or the true intersection, the true circumcenter. Does that make sense? I'll have something that's really close to it, but I won't have the true circumcenter. And that's what we're looking for. That's why rounding is kind of bad in this course. Okay? We want to leave things as fractions. So the rest of the worksheet kind of walks you through that process again, but now for points A and C. So points A and C are 4, 2. So do that over here. A is 4, 2. And C is -2, -2. Okay, just to save a little bit of time, what did you guys find for the slope of A to C? 2 over 3. Okay, so that slope is 2/3. And then the slope of the line perpendicular to that should always be what? -3 over 2. Remember, that's again the opposite sign reciprocal, right? The midpoint of AC. Add these two things together, divide by 2.
0.
Careful. Careful. 1, 0. So it gives me a +2. +2 divided by 2 gives me a 1. These go to 0. 0 divided by 2 is 0. So now, again, we're dealing with AC here. We just found the midpoint to be right there, 1, 0, and that looks pretty accurate, right? We said the slope of anything perpendicular to AC should be -3 over 2. So I'm going to go down 3, 1, 2, 3, and then over 2. So it gives me there. And then I would go up 3 and maybe left 2. So it gives me that. And now I will take my line, my straight edge, my ruler, whatever, connect those. And we see that blue line looks like it's probably the perpendicular bisector of AC, right? So it's confirmation that we've done things correctly. Now, here's the thing about the rest of this worksheet is I asked you to go through and find the perpendicular bisector of CB as well, right? But don't you know where the blue line and the red line intersect, that the perpendicular bisector of BC is going to intersect at the same spot? Talk about that a lot, right? So, in regards to on a test or quiz, do not find all 3 of them. It's going to waste time. Okay, just deal with 2 of them, unless I prompt you to find all 3. But finding 2 is sufficient. Now what we need to do is find the equation of that blue line. Well, we're going to go y minus y1 equals m times x minus x1 again. This is your x1, y1, and this is your m. So we go y minus y1, 0, and then negative 3/2 times x minus 1. Now when y minus 0, that's just y, right? Distribute, I get negative 3/2 x, and then plus 3/2. There's my equation of this blue line. Okay. I asked you to do the exact same thing then for B to C. B being the point 6, negative 4. And C again being negative 2, negative 2. If you find the slope of BC, you got what?
1/4. Negative 1/4.
Negative 1/4. And then the opposite sign reciprocal of that should be 4. And now the midpoint, add those 2 things together, divide by 2 gives you 2. Add these 2 things together, divide by 2 gives you negative 3, right? If I go up there, plot 2, negative 3, 2, negative 3, right there. And then from there, go up 4 over 1, up 4 over 1, and maybe connect those. Would you agree that green line goes through the same point where the blue ones and the red ones cross, right? All right, so our circumcenter. I don't know what it is. It usually is not going to be a really nice number here, okay? It's very rare that your 3 ordered pairs for your vertices are nice whole complete integers, and then your circumcenter also comes out to nice clean integers, okay? Your circumcenter is probably going to be a nasty set of ordered pairs. It's just the nature of the problem. But I do know, looking at that thing, my x value is going to be what kind of number? It's going to be positive or negative for my circumcenter. Positive, right? So my circumcenter is going to be this point where my cursor is, right? And to get there from 0, 0, I have to move to the right first, right? So my x value is going to be positive, but my y value is going to be negative. So that's a little bit of insight to tell me the next set of steps that I'm going to go through when I get a solution. Does that solution match with what I think I should get? Okay. I also kind of know that my solution probably isn't going to be, or shouldn't be. Let me zoom in a little bit here. If I can, view, zoom 200. When I get a solution, okay, this point where my cursor is a little bit bigger than 2, a little bit less than 3, right? So the x value. So my x value should not be any bigger than 3. My y value looks like it should not be any bigger than probably negative 3. Does that make sense to everybody? So I got a ballpark idea using my graph of what my solution should look like. Okay, and then we'll see then if that then is maintained as we go through the rest of this algebra. So the rest of the algebra said that you have 3 equations. You have y equals 1/3 x minus 8/3. We had one that said negative 3/2 x plus 3/2. And then we had another one that was 4x minus 11. Okay, those are our 3 equations, right? So that's all the work we went through. Because what we're going to do is we're going to say Algebra 1 taught us that if we have 2 equations, okay, that provides us 2 graphs, And we can go through the process of substitution to see where those two lines intersect, where they agree algebraically in regards to an x and y value. Okay. So if I want to see where maybe the blue and red lines intersect, or the blue and the green one intersects, or the red one and the green one intersects, all I have to do is take their respective equations and set them equal to each other. So let's say that I want to deal with, I think we did the blue and the red one first, right? So I would take maybe these two. Those were the first. I know the colors are messed up, but take those two, set them equal to each other, and I should be able to solve for x. Or I could take these two, set them equal to each other, and solve for x. Or I could take the first one and the last one, set them equal to each other, and solve for x. Okay? I'm a person, I look at this, and I always try to think, and hopefully you do this as well, of equations that knowing I can choose any two of the three, I like to choose the two that maybe are the simplest. Do those look kind of simple? The last one, 4x minus 11, I like that one because it's all whole numbers. Okay, all integer. And I like the middle one because I deal with halves better than I deal with thirds. Okay? So I'm going to take those two. And if we're saying these two lines concur or they agree at some x value and y value, that means that at some point those y's are the same. So then it means that these expressions here need to be the same as well. So I'm going to take negative 3 halves x plus 3 halves and set that equal to 4x minus 11. That's the substitution technique that we learned last year with systems of equations. What can I multiply everything by to get rid of the fractions? 2. So when I multiply this by 2, I get negative 3x. Multiply this by 2, I get plus 3. Multiply this by 2, I get 8x. Multiply this by 2, I get negative 22, right? Now we're down to like a first week algebra question. Add 3x to both sides. Add 22 to both sides, so I get 11x to be 25, so x ends up being 25 over 11, right? Now, does that simplify? No, 11 is prime, right? And 25 is not divisible by 11. So, leave it as 25 over 11. Do not change that to, 2 point something. Okay? Just leave it as 25 over 11. Because we're going to use that number to find the y value of our circumcenter. If I change that to a decimal, that decimal is going to have to be rounded probably. And then when I plug that rounded value back in to find the y value in the circumcenter, I'm really not finding the y value in the circumcenter. I'm finding something very close to the y value in the circumcenter. I want the exact one. So leave it as an exact 25 over 11. Okay? And most generally speaking, your numbers that you find for your circumcenter are not going to be really nice whole numbers or integers or anything like that. Okay? So we know from systems of equations then that if I used those two equations to find x, I should be able to plug my x value back into either one of them to find y, right? Does it make sense to plug it into this bottom one maybe a little bit better than the top one? I'm going to take this x and say that y is equal to 4 times that x of 25 over 11, then minus 11. 4 is 4 over 1, right? How do I multiply two fractions? Nope. Top times top gives me 100, right? Bottom times bottom gives me 11. Minus then 11 over 1, right? Well, how do I subtract two fractions? Common denominator. What's common denominator going to be here? 11. So the top becomes 121. Okay? So 121 over 11 is still 11, right? But now I can actually do the subtraction. And this is going to give me, the denominator stays 11. What's the top going to become? Negative 21. Does that reduce any? Yes. Oh, careful. 11 is prime, so 11 only divides by 1 and 11. Do either of those numbers divide negative 21? No. 1 does, but doesn't really provide anything new. So y value ends up being negative 21 over 11. Okay? So our ordered pair, our solution, the whole reason for doing this problem is to find this ordered pair of 25 elevenths comma negative 21 elevenths. Okay? You have the ability to check this. Okay? Even if we don't use technology, we should be able to realize, and I'll do this real quick for us. Let's say that I wanted to check this thing. Don't we know that these two equations better be equal as well? So if I take the top 1/3 x minus 8/3 and set that equal to negative 3/2 x plus 3/2, that is now looking at maybe I think it's the red line, the red line and the blue line, where we initially used the blue line and the green line, the red line, what we just did, the two equations we just used were the green line and the blue line, okay? So if I take the red line and the blue line and set them equal to each other, I should still get the same x and y values, right? Does that make sense to everybody? So doing that, what would be a nice number to multiply everything here by? If I multiply everything on the left-hand side by 3, I'd get rid of those fractions, right? But does it get rid of these 2's? No. But if I multiply everything on the right-hand side by 2's, it gets rid of those 2's, but not the 3's, right? So what should I multiply everything by? 6. Okay, the 3 times the 2. So multiply everything by 6, it gives me 2x minus then 16 is equal to then negative 9x and then plus 9, right? Okay. I'm going to add 9x to both sides, so I get 11x. Add 16 to both sides, I get 25. Does x still end up being 25 over 11? Same thing we found using different equations, right? Now, I'm not going to do this, but I'm pretty confident that if I plug that x back in to find y, I'm going to get negative 21 over 11, right? Okay. Again, having the picture is useful as well, because 25 over 11, pretty close to 2.5, right? Okay. Well, if I look at my picture over here, didn't we say that we were going to be between 2 and 3 for our circumcenter? And if I look at negative 21 over 11, that's pretty close to negative 2, and that's kind of where my circumcenter looks like it's positioned. Is that doable for everybody? All right. Now, here's what I like, because I want you to be able to do this. I want you to, at some stage in your mathematical lives, be able to do the work by hand, but also use something to show me that I've done everything correctly. Okay. So I'm going to take GeoGebra. I'm going to plot these points. 4, 2, 6, negative 4. And negative 2, negative 2. Gives me that triangle, right? Okay. Find the perpendicular bisectors. Gives me those two things there. Okay. Now I'm looking for the intersection of those two things. So I asked GeoGebra to do that, and it gives me this point right there. Now that point, 2.27, comma, negative 1.91. It's not the greatest way the way it's written, because it's not a really nice number. Okay. We changed around and we see that it repeats, so it's a rational thing. But if you take your 25 elevenths, 25 divided by 11, does that number right there give you the x value that GeoGebra found? And now if I type in negative 21 over 11, that number right there is the y value that GeoGebra found, right? Okay, so we know we have the right circumcenter. Where if you started using fractions and took those fractions and rounded them to nice decimals, you're not going to find the right circumcenter. You might find something kind of in the ballpark of this thing, but you will not find the exact circumcenter. We just found the exact one. Okay. Does anybody have questions over this? I know it's a long process. Okay, but if you take the time to learn the process and learn the individual components of the process, you can do it relatively quick. Okay. Some of you.